Hello, VLSID audience. My name is Ahmedullah Aziz. I am an assistant professor of electrical engineering and computer science at the University of Tennessee, Knoxville. I'm sorry that I couldn't be there in person because of some unforeseen and unavoidable circumstances. However, I'm excited to still be able to talk to you virtually through this recorded and pre-recorded lecture. My presentation will be on a unique topic, I should say. It's related to superconducting electronics. When we talk about electronics in general, the first thing that comes to our mind would be semiconductors, not necessarily superconductors or other types of materials. However, hopefully through this tutorial, I'll try to convince you uh, about the necessity of paying attention to the superconducting electronics paradigm, given the circumstances around us. So without further ado, let's get started. Before I begin with the technical part, I would like to quickly introduce my research group. My research group at the University of Tennessee, Knoxville is known as Nanoelectronic Devices and Integrated Circuits Lab, or in short, Nordic Lab. Uh, our research focuses on exploring uh, novel materials and finding ways to use them in practical electronic applications. So through my research, I try to find unique ways to harness the properties of materials like superconductors, ferroelectrics, or others, and envision unique devices capitalizing the properties of these materials, and then see how those devices can be utilized to reimagine some existing circuit topologies. So I do a lot of device circuit co-design. And eventually, we always try to tie our circuit level innovations to the system level application, like, for example, high performance computing or neuromorphic computing or AI in general, and see how they benchmark against the existing cutting edge. Because without doing so, you don't know which technology will give you diminishing return. Because it's easy to say that we are going to use so and so novel material, but it's not really easy to justify the economics behind it unless you do proper benchmarking and the numbers look convincing. So that's what we do. We do a lot of co-design across multiple stacks of electronics. Now, in terms of topical overview of my research, I try to divide it up into four categories. On the top left corner, you see compact modeling, because that's what we do a lot in our group. We try to make physics-based as well as non-physical, phenomenological, machine learning powered compact models for emerging and exploratory materials, ranging all the way from superconductors to semiconductors to 2D materials to oxides and so on. Anything that has interesting properties that is worth making a model for, we would be happy to work with that. On the other hand, uh, we have a special interest in memory and peripheral design. I can talk about why memories are getting a lot of attention, why they're going to be game changers in the next few years or so. However, this talk is not meant for memories specifically, but just wanted to highlight that we do a lot of memory design and specifically peripheral design for memories. Cryogenic electronics is going to be very relevant to my talk today, and that's why I'm not going to talk too much about it right now, because the rest of the talk will focus on this section. And last but not least, many of our work caters to the needs of analog electronics. And when I say analog, it is not necessarily just traditional analog circuits like amplifiers. It is, for example, non-Boolean computing paradigm, where you use coupled oscillators to compute. And this is a fully analog system. It could also be neuromorphic computing system where you use brain-like architecture instead of conventional, deep learning-based AI approaches. And we have a lot of interest in this type of analog electronics in general. So setting all this aside, I will be talking about a topic that caters to the needs of three unique transformative technologies in our community. And these three technologies are quantum computing, high performance computing, and space electronics. If you're wondering how they're linked, I mean, they seem to be very disjoint from each other. I should say the common thread that connects the three of them would be superconducting electronics. And I'll talk about how they're connected, how they can all benefit from superconducting electronics in general moving forward. So here is an overview and outline of my talk. I'll start with some brief background and motivation to hopefully convince you uh, about the needs for superconductors in electronics. And then I'll talk about some specific challenges in the existing state of the art. After that, I'll focus on superconducting Boolean systems because we're mostly used to seeing Boolean, systems, digital electronics in general. However, as you must have been hearing a lot throughout this tutorial, beyond Boolean computing has a lot of promise. So I will also point you towards some superconducting non-Boolean systems as well. And towards the end, I'll try to give you an overview of what's beyond superconductors. There are materials that are like superconductors that are dissipation free, but they're not really superconductors. And they also have some unique, you know, benefits to electronics. And I'll try to briefly touch upon that direction as well. And then finally, I'll conclude. So let's get started. Well, I'll start with some really stark warning about the AI and high performance computing systems that we are all using around us. We all like to use chat GPTs and other AI systems that are very powerful, but the reason why they're so powerful now is because our computational power, or in other words, high performance computing capabilities have progressed dramatically. We can handle a lot of computation within a very short period of time, but that comes with a cost, and that cost is energy. Okay? If you follow the area more closely, you'll realize that most AI systems take up a lot of energy in different form. Very recently, New York Times published an article where they talked about how AI could soon need as much electricity as some countries. And the countries that they quoted, they're not like small island nations. They're countries like the Netherlands, Argentina, and so on. So if you could imagine that an AI model, AI system taking up more electricity than in an entire country just to, perform some random tasks that you may or may not really think about, right? This is fascinating. But that's not the end of the story. The story gets worse, essentially. If you see this chart on the right, which was published in a Nature paper in 2018, so it's pretty old data right now. It shows almost an exponential increase in the energy demand, and specifically driven by the data centers. If you see the green zone, the data centers are going to take up a lion's share, a significant proportion of the overall energy demand in our, civilization, essentially. And we are not going to reduce the amount of data that we generate anytime soon, because look at the other chart. This is basically a projected picture of how much data we'll be generating over multiple years. This is easily going to skyrocket pretty soon. And that means the energy demand that these data centers are, you know, projected to require is only going to get worse over the years. So we have to think about it. How can we handle this much, energy demand across high performance computing without curbing the rapid progress of AI and other capabilities? We don't want to give up our AI capabilities, but we don't want to deplete our energy resources rapidly and, direct or redirect energy resources from all the other sectors just to power these AI systems, right? So we have to think of a radical solution. Conventional semiconductor-based electronics have their own limits in terms of energy efficiency, and we are very close to getting to that limit. We cannot really do a whole lot, uh, to curb this rapid exponentially increasing energy demand per se in electronics. So we have to think completely out of the box. Here is one potential solution that I want to pitch. That is superconducting electronics. Just look at the chart on the right. On your right, the green zone shows the typical power delay numbers for CMOS electronics. And you don't have to look at the specific numbers, but just compare the relative quantities with each other. SCE stands for superconducting electronics. So this orange, oval-shaped region that you see, it shows the typical range of power delay requirement for superconducting electronics. And you can clearly see that there is there is orders of magnitude reduction in the delay and power numbers when you switch to superconducting electronics from CMOS paradigm. So that gives you a lot of hope. So that means if you could somehow, get to superconducting paradigm platform, computing platform, you'll be saving a lot of energy in general. However, I know what you're all thinking. Aren't we spending a lot of energy trying to cool things down to make them superconductors? Well, if you're thinking about it, you are right, because superconductors, for the most part, most superconductors require cryogenic cooling and often below 4 Kelvin or around that number. So you'll be using liquid helium, not liquid nitrogen. So it's pretty expensive, to be honest. However, what you have to keep in mind is it is more like a fixed cost. So just imagine getting into a theme park where you have to pay an entrance fee, and there are multiple rides that you can use, and you can use them unlimited times, right? So if you just get into the park and don't really use any of the rides and just walk around, you're not gonna really, you're not going to be making a good decision in terms of finances, for example. Like, okay, it's not beneficial for you. But if you get in, use the fixed cost, and then use the rides to the fullest extent, right? The more rides you use, maybe all the rides are, super cheap after you get in. So that fixed cost will not really look as bad if you save money at every ride in the theme park. Okay, so similar to that, when you use superconducting electronics, you pay a fixed cost in terms of energy, in terms of liquid helium cost, and so on. And then once you pull things down, at every computing stage, you save orders of magnitude energy. And if you do a lot of computation, then your fixed cost remains the same, but your dynamic cost, or cost at every computing stage, rapidly reduces, and you win eventually. You easily break even and then go beyond the break even point. So that is the big picture of using superconducting electronics. It only makes sense when you go for high performance computing or large scale computing system. All right. It is basically, it's not science fiction if you're thinking about it in form of something super futuristic. People have been using superconducting electronics for many reasons for decades. It's literally decades old. But this is a more recent example. This is a microprocessor made out of superconducting devices, uh, from Japan. And very recently, IEEE Spectrum highlighted this work because they experimentally demonstrated 80 times less energy demand than semiconductor-based microprocessor for AI workload. Yeah, so this is real number. And they accounted for the cooling cost, by the way. So there you go. There are realistic hardware available today that can demonstrate the overall benefit, but it is obviously a small scale prototype. It's not going to do too much when it comes to systems like, say, ChatGPT or others. However, it clearly proves the point that if you could scale up your superconducting electronics to the server level or hyperfast computing level or supercomputer level, that means you make superconducting supercomputers, hopefully the numbers will make even more sense. All right. So that's the big selling point. However, it's not always about the raw computing numbers. There are some applications where it makes sense for other reasons. And quantum computing is such a scenario. Let me explain. So in a conventional quantum computer, a very simplistic picture of a conventional quantum computer is what you're looking at right now on your right. You have three components. One is the like the qubit substrate or the quantum substrate, where you have the qubits, which are the crown jewel of the quantum computer. You must be hearing a lot about qubits mostly. And for most of these systems that are developed by commercial entities like Google or IBM, they use superconducting qubits, and they require cryogenic cooling down to millikelvin. So it's pretty cool. And then you need to use classical control processor and classical memory to control this qubit substrate. And what do I mean by control? You have to program these qubits, you have to read them out after the computation is done. So basically, most of these are handled using classical circuitry. And these control circuitry are kept typically at room temperature. The processor, the memory, they are at room temperature. And then you have to interface between this control circuitry and the qubit substrate using uh, interconnects, which are mostly coax cables, and they're they are creating a lot of thermal noise. Here is how. So your control processor is at room temperature, 300 Kelvin. Qubits are at millikelvin. So there is a huge thermal gradient, and the thermal gradient injects thermal noise into the qubit system, which is already very sensitive to noise. The reason why we cool them down so much below a Kelvin is because we try to reduce noise. But while trying to program them or read them out, you're injecting a lot of noise into the system, which is already very, uh, sensitive to noise. So you're not helping this. And by the way, these coax cables cannot really be scaled up to more than 1,000, for example, because very soon your noise level will completely flush out the qubit performance. So this is not scalable. This is good enough for maybe proof of concept demonstration, but if you try to do something realistic, something that will really be applied in our practical situations, you have to have more than 1,000 qubits, and if, even beyond that. And for systems like this architecture will no longer work. Uh, by the way, this is just another picture of what I just explained here. You have cryo refrigerator, and within the cryo refrigerator, you have the qubit substrate. Okay, and control circuitry, like classical control electronics, for example, they are all outside the cryo refrigerator. Now, the vision is if you could bring everything, the processor, memory, the control part, for example, within the refrigerator that the qubits are in, you could significantly reduce the thermal noise because of reduced thermal gradient, but also you could then use superconducting interconnects, which will be lossless. So it will not really inject that much noise into the qubit systems. And then you can scale them up because you're no longer using coax cables, which are really bulky, right? So the dream solution would be to bring down the control processor and the memory, or in general, the control electronics below 4 Kelvin temperature, because that's where you can get superconductors act as superconductors. Uh, I hope you see what I'm hinting at. So you make processors and memory out of superconducting materials and make them operate below 4 Kelvin, and you use superconducting interconnects to interface with the qubits, and thereby you create a platform, a quantum computing architecture that will not suffer from thermal noise as much, and it will be scalable to practical levels. So that is the vision that we are working towards, and not just us, many research groups as well as industry folks are working towards. So there you go. This is one more selling point for superconducting electronics. Um, well, I have a couple of other slides that talks about memory specifically, because oftentimes when I talked about AI, I just spoke about computing. So basically processing. You might be getting this notion, it may not be that clear, that you just need to make processor, superconducting processor, which is not the case. You also need superconducting memories, because obviously there is no useful computing without storing that information. So you need memory as well as processors. If you're wondering how classical memories could be used in quantum computers, here is an example for you. Uh, Quantum algorithms require large number of arbitrary rotations, and that require large program memory. Uh, Also, um, to maintain data integrity of the qubit states, you need to do continuous error correction, and that process also requires large data memory. And both of these require essentially high capacity digital binary memory. So classical, essentially. So you need classical memory even in quantum computing. And obviously for AI systems, you still need classical memory. Last but not least, I will be very brief about this particular slide, which is aerospace application. If you look at the temperature of deep space, it is below 3 Kelvin. Okay, so you are literally looking at a natural environment for superconductors to behave like superconductors, essentially. So space is a sector where superconductors will possibly not require any specific cooling cost or require very low cooling cost. So it makes a lot of sense to consider using superconducting electronics for space exploration related hardware. And that's where they have been mostly used, by the way. A lot of work was done by NASA and others in the past. And I'll briefly touch upon the history of superconducting electronics, and you'll see. So it's a no-brainer. It's useful, but it's a very small niche. So I'm not getting into the detail of this direction too much. Okay, so Let's talk about the state of the art. Let's talk about how the superconducting electronics look like right now in today's world and talk about the existing challenges. Okay. So, as I told you before, it's not a new idea or a new paradigm of engineering. Superconducting electronics have been there for literally decades. So on the top side, top portion of my slide, you're looking at what happened with superconducting memory specifically. And in the bottom half, you're looking at what happened to superconducting processors over the years. So as you see, memories and processors have been continuously studied and tested and developed with superconducting technologies for many years. So it's not a new technology or new concept in any way. But why don't we have super large-scale superconducting systems today? Because despite our best efforts, uh, there still remains significant challenges that we couldn't really get over yet. Okay, so I'm not going to go through the individual uh, challenges for all of these technologies because that will simply be an overkill. But I encourage you to read this review article if you can, or there are other nice book chapters and review papers available online. I'm happy to share any other resources if you're interested, but I'm going to skip over all of this and condense them down to just one slide. I want to talk about the three big challenges that still remains. Well, there are many other challenges that people somehow solved in one way or the other, but these three challenges still remain. So to explain those challenges, I want to direct your attention to the top uh, four blocks, right? As you see, uh, if I ask you, what do you see? These are all superconducting circuits, okay? And in those superconducting circuits, uh, what is a prevalent component that you see more often? Do you see more resistors? Do you see more capacitors? Do you see more transistors or something else? I mean, if I were you, I would point out inductors more often because in every circuit, you have inductors, as you see. And if you know, if you're aware of chip design practicality, you know, inductors are not really that scalable for many reasons. They're bulky and also they have issues with, you know, coupling. So you have to space them out. Otherwise, there will be residual coupling between inductors. So considering that, inductors will be nightmare to scaling. But superconducting electronics, since they have superconducting devices provide zero resistance when they're superconductors, it is difficult to deal with them with regular approaches that we are aware of. For example, just imagine if there is zero resistance when you apply a voltage across it, and you know the voltage source will see zero resistance. So how much current will it generate, right? This is a good question if you think about it. So you cannot really use superconducting electronics using the conventional circuit biasing approaches. There are specialized biasing approaches that we use. I'm not getting into that right now, but we'll talk about it soon. So uh, for the unique nature of superconducting devices and circuits, we need a lot of inductors, and those inductors are not scalable, but we still remain bound to use inductors to make them work. And what you're looking at here are essentially memory cells. So every block that you see here, I hope you can see my cursor, uh, they are a single memory bit cell. So if you're, you know, if you have some practical knowledge about memory cell design, you know, scaling them down is a crucial necessity for us. We need to make sure that the memory bit cells are as small as possible so that we can store a lot of bit, because storing one bit doesn't make any sense, of course, right? So you need to think about millions and billions and trillions, essentially. So the smaller the cells are, the more storage capabilities you have. And that is a challenge for superconducting devices because they're so reliant on inductors, which are not inherently scalable. So getting practical level of memory density remains a challenge. Okay. If you're wondering, these cross symbols, they represent Josephson junction, which is a superconducting device that is widely used, by the way. Josephson junctions are used as qubits in most quantum computers, but they're also used in classical superconducting electronics that are not quantum, by the way. All right, I'm not getting into the details of these existing technologies because there are more interesting stuff that still remains, which I will talk about in my slides, in my upcoming slides. But I hope you understand this first challenge, the necessity of using inductors in superconducting circuits. The second challenge that I want to highlight is uh, the use of current biasing. So as I just explained, since you have zero resistance in superconducting devices when they're superconducting, if you apply a voltage, basically, or if you think about two resistors in series, you apply a voltage, there is voltage division between these two resistors. But if one of them becomes zero, it no longer takes up a share of the voltage, right? The other resistor will take the entire share. So basically, driving a superconducting device with voltage biasing is practically impossible. Okay, so the way we do it is we use current biasing to control these superconducting devices. And current biasing has an issue. Think about a voltage source. When you connect a voltage source to multiple nodes, all of those nodes will have the same voltage, ideally. All right. But when you connect a current source to multiple branches, all of those branches will take a share of the current. So the current will distribute across branches. It will not be equally distributed. It will not be equally copied across all the branches, as you can see. So when you use current biasing, you have to, for example, when you try to drive a block of circuit, superconducting circuit, with another, and you're using current biasing, every time you drive a stage, maybe say, for example, this block is driving three other blocks using current, every block will get a portion of the overall drive current, not the entire drive current, as you see. So you have to use repeaters or coupling components to regenerate the current level. Those components take up additional area, and that becomes a nightmare for scaling to practical levels. Okay, so if you're just trying to make a prototype and show that it works, that's fine. But if you're trying to do something practical, then it's a major challenge, and it remains a major challenge for most superconducting entities. All right. Finally, this is also linked with the previous point that I told you about low resistive state, meaning when superconducting devices are superconductors, they have zero resistance, but also most of these devices have really low driving capabilities. So it's difficult to drive an output. And when you have challenge driving an output, that means you have challenge cascading. If you know something about Boolean logic, you have to basically cascade, like ideally to infinite level, basically as many stages as you need. Uh, Practically, maybe not much, but at least, theoretically, you should be able to keep creating branches, right? Without diminishing your overall voltage levels or rail to or sacrificing your rail to rail swing. But that is difficult to achieve with superconducting devices. So that remains a challenge. All right. Now, with those ideas in mind, I'm not getting into the nitty-gritty details of all the other challenges. These three are easy to explain and easy to relate to. That's why I chose to talk about them. Let me talk about how we are trying to reimagine in our group and in many other groups, how we're trying to reimagine superconducting logic in memory. That means we're looking at the Boolean paradigm per se, where you have binary logic and you have binary memory elements. Okay, so let's talk about how we are trying to find solutions to the problems I discussed. So in our group, we are looking at emerging superconducting devices rather than conventional superconducting devices like Josephson junction, for example. So um, we are always interested in finding interactions between multiple materials because that's where a lot of new discoveries occur. And I'll show you in this slide three unique materials, three unique devices that we have explored in our group so far. Number one, on your left, the ferroelectric SQUID, where SQUID stands for Superconducting Quantum Interference Device. It's a mouthful. It is essentially two parallel connected Josephson junction. If you do not know what a Josephson junction is, it is a superconductor insulator superconductor junction. So basically, it's like a metal insulator, metal capacitor. The uniqueness here is that the metal is a superconductor. And remember, it only behaves as a superconductor below a certain critical temperature, which is typically, say, 4 Kelvin. So you have a MIM structure, metal insulator metal structure, where the metal is superconductor, and you have two of them in parallel. So basically, parallel connected Josephson junctions is called a SQUID, or superconducting quantum interference device. And what we have here is you have a ferroelectric layer underneath the SQUID, where the phenomena of ferroelectricity interacts with superconductivity, and they create an interesting rich dynamics. All right. And what is that dynamics? So you may know that ferroelectric materials can have positive and negative polarization. and they can hold on to those polarization in a non-volatile way, meaning you don't have to continuously supply external voltage to maintain the polarization. If you remove the voltage, it will get stuck at either positive or negative polarization. All right. Uh, and next time when you start, it will start from that definite polarization, either positive or negative. So depending on the polarization of the ferroelectric material, uh, the characteristics of the top squid layer changes. All right, let me go over the blue curve first for yourself. So the blue curve shows uh, the IV or current voltage characteristics of a typical squid device, where you see in this region you see zero voltage but non-zero current because your resistance is zero. If your resistance is zero, even if a current is flowing through it, the voltage across it will be still zero, as you can see. So up to a critical level, which is right here, up after this critical current level, your squid devices no longer stay superconductors. Remember, superconductors are superconductors below three critical level: below a critical temperature, below a critical current, and below a critical magnetic field. All right, we're just talking about the critical temperature mostly here, but we shouldn't forget the other two. So here you are looking at the signature of what happens when you exceed the critical current, right? So when you exceed the critical current, it gets out of the superconducting mode and starts creating a voltage across it because it has a resistance now. And same thing appears on the negative opposite polarity of the current. So it creates a negative polarity of voltage. All right, now compare the blue one with the red one. The only difference you see here is in the critical current levels. So in one of them, you have a higher critical current. On the other, you have a lower critical current. So basically, depending on the positive and negative polarization level, you can have two different levels of critical currents in a squid structure. So you have literally taken in a squid and you have made it more like a non-volatile device that responds based on the polarization stored in the ferroelectric material. All right. And we'll talk about the use case for this particular material or this particular device structure soon. But this is a unique device that we were really interested in exploring. The second one on your right, excuse me, you're looking at something called a superconducting memristor. Many of you must have heard about memristor. It is a resistor with a memory. So it can have low and high resistance state, and it can remember whether or not it was in low resistance state or high resistance state in the previous cycle. So every time you restart with applied voltage or current, it will start with either low resistance state or high resistance state accordingly, right? So that's the memristor. A superconducting memristor is almost similar, but the only exception here is the devices that you are using to make that memristor are themselves superconducting. So for example, here you have a Josephson junction, you have another Josephson junction. So this is essentially a squid structure, but this is a very special type of squid known as a CA squid, conductance asymmetric superconducting quantum interference device. So even longer mouthful, if you think about it. But anyways, so this is a superconducting device that behaves like a memristor. If you look at the current voltage characteristics, you see a typical butterfly loop, which shows you have a high resistance state loop, you have a high resistance state path, you have a low resistance state path, like a memristor, and you can access them in a non-volatile way. So this is essentially a memory device by itself that you can use. All right. The third one is a heater cryotron. Cryotron is more like a three-terminal switch, almost like a three-terminal switch, where you have a gate and you have a channel. When you flow current through the gate terminal, and the gate can be a non-superconducting metal, or it could be a superconducting, but you make it non-superconducting by injecting really high level of current so that you exceed the critical current level. So when you flow current through the gate, it hits up because it's resistive. So you have this I square R drop. It hits up, and that heat increases the temperature of the channel, which is not physically connected, but it is very close. It is separated by a small layer, a thin layer. Okay, so the heat gets through the thin layer to the channel, and gradually the channel heats up and it exceeds its critical temperature. So the channel was initially superconducting, but when you increase the temperature beyond the critical temperature, it becomes resistive. All right. So that's how, by controlling the gate current, you could either uh, keep the channel superconducting, or you could make the channel a resistor. Okay. So this is a switch that is controlled by gate injected current, essentially. So this is another unique superconducting device. The reason why I chose to talk about these three devices today is because I'll show you some of our recent works where we made use of the collective interactions between these devices to achieve logic and memory. So the first one is an example of a reconfigurable logic. And what do I mean by that? So this is the device that I just explained. This is a heater cryotron. This is the gate terminal that I spoke about. This is the channel. Uh, Look at this illustration here. When you flow current through the gate terminal, and there is a region which is really narrow, and that is deliberate because we want to generate heat and we want to concentrate the heat close to the channel. Okay. So when you flow current through the gate, it creates heat, and that heat is distributed across the channel. And once the channel becomes fully resistive, you kind of uh, you see a dramatic change in the channel current, right? Uh, Whereas, like, if you only switch from a low resistance state to high resistance state, you don't see such a dramatic change. But when you switch from zero resistance to a non-zero resistance, the change is really dramatic, right? So it's very useful and easily detectable. Okay, so this is a symbol for the heater cryotron device that I just explained. This is a device that we fabricated with our collaborators at NIST. And, this is a cartoon to explain its properties. And this is a symbol so that we could easily draw the circuits. Okay. So using this device as a single entity and some unique biasing approaches, we managed to achieve multiple logic operation, Boolean logic operation using the same device. Okay. So what you're looking at here is a copy gate, essentially like a buffer, or inverter like a not gate, AND gate, OR gate, and majority gate, all using the same device here. And I'm not getting into the detail of it. The details are available in our published work. However, I'm just giving you the high level picture here. Remember, it is still a current driven memory. So there are repeater concerns, but what you don't see here are inductors. So it is a non-inductive uh, superconducting logic, which is very unique. There is another interesting feature in this logic design approach. First of all, if you remember, we are using the exact same structure to incorporate different types of logic gates. And if you closely look at the types of logic gates we are able to incorporate, you can essentially make NAND and NOR operation. And NAND and NOR are basically universal logic gates. You can use that to incorporate any random Boolean logic. All right. And that means any type of logic that you try to make, you have the same type of blocks. As opposed to that, when you look at CMOS approaches, obviously this is not the best way to design as CMOS based layout, but this is here to make a point. So basically when you look at the layout, you can easily understand that this something is an AND gate, the other thing is a NOR gate. You could easily reverse engineer based on the physical layout, all right? Because they look different. You can say that, hey, this is an inverter, and so on. However, in this approach, since every logic gate looks exactly the same, you cannot tell which one is a NAND gate, which one is a NOR gate, which one is an inverter, and whatnot, right? So that's why this is naturally camouflaged. And when something is naturally camouflaged, that has a lot of benefit in terms of hardware security. So this is another feature that I wanted to point out. Okay, so we managed to get a superconducting logic family without inductors. So we solved the problem. And then in doing so, we happen to stumble upon an additional feature of camouflaging. So that is, an additional bonus. Now, let me switch gear to a completely different way of designing logic using some voltage control superconducting uh, devices. And if you remember properly, current control was a challenge, and we couldn't get rid of that challenge in the first approach. We managed to get rid of the inductors, but not the current control, current bias. But here, when we studied the ferroelectric squid, we realized that ferroelectric materials can be, manipulated with voltage. And when you do so, these ferroelectrics directly impact the properties of the squid, which are typically driven with current. So instead of driving the squids directly, why don't we drive the ferroelectric layer with voltage and then let the ferroelectric interact with the squid and then incorporate a logic, circuit accordingly. So we envisioned four types of logic gates. Again, and or not. When you see and or and not, you understand that you can essentially get any type of random Boolean logic, right? What you're looking at here, they are symbols basically. So this is the symbol of a ferroelectric suite. This is the symbol of heater crackdown. So essentially, we have coupled both devices in a unique way to achieve this uh, copy gate feature or not gate feature, an AND gate feature and OR gate feature. As you see, they are not all the same. So it's not like the other approach where everything looks the same. There is no camouflaging here, obviously. We were not looking for camouflaging anyways. We're just trying to incorporate generalizable Boolean logic family, all right? And interestingly, notice the gate terminals are driven by voltages, not current, okay? So this is essentially a voltage controlled logic family because the inputs are all voltages and the output will also be voltage. So you can directly drive one stage with the other. And when we designed this, we had to make sure that you have the same voltage levels at the gate inputs and the output. So you have rail to rail swing everywhere, like the CMOS logic gates. So this has all the features of a CMOS logic gates and some additional features that superconductors provide. So this is basically bringing the best of both worlds: voltage controlled and cascadability from CMOS, and superconducting properties from the superconducting devices that we're using here, like the cryotrons and the superconducting squid. Okay, I'm not getting into the detail of their working principle here because all of these are available as public knowledge in our published work. I'm happy to forward any of these papers to you. I want to highlight in this slide the beauty of voltage control, which we often take for granted. So in CMOS-based design, what we are all aware of or used to seeing is you have Boolean logic gates, you cascade them, you incorporate any random Boolean logic the way you want, right? So you could treat this superconducting logic family almost similarly. For example, this is a NOT gate, this is an AND gate, and so on. You could incorporate this simple Boolean circuit using the logic gates that we have designed here. And these are cascadable because they are voltage based. You don't have to create splitter circuits for current control logics, like the case for current control logic systems, all right? So this is a very big benefit that people have been looking for in superconducting world for a while. Now, by the way, this paper is published in Journal of Applied Physics by now. It's no longer just an archive preprint. Okay, so we also realized that, hey, this ferroelectric squid is not only a possible logic device candidate, it is also a memory by itself because ferroelectric material is a non-volatile entity. You could somehow, program this ferroelectric into positive and negative polarization. And then if you find a way to read it out, there you go, you have a memory. And the plan that we put forward was to read it out using the squid structure and writing it through the ferroelectric gate, as you see. And the way we did it is if you go back and try to recall the discussion about the IV property of this ferroelectric squid, we created two critical current levels. So the corresponding to the positive and negative polarization of the ferroelectric, the squid structure was switching to resistive mode at different current levels. So if you see this bluish region here, if you bias your squid structure in this region for negative polarization of the ferroelectric, you will still be in the superconducting mode of the squid. But for the positive polarization of the ferroelectric, which is shown as the dashed red line here, you'll be exceeding the critical current limit and you'll be operating in the resistive mode instead, not superconducting. So by biasing your device using this ID level, you could selectively understand whether it was storing positive polarization or negative polarization. So that means you can read out the memory electrically. So this is a way we chose to do so. So basically, this is the memory array. By the way, one challenge that I often observe in our superconducting electronics domain is that people often just report a memory cell and be done with it. They say, oh, you're storing two states, so that it's a memory, of course. But the thing that I want to highlight is it's not really a useful memory if you cannot envision an array structure, because memories require location, address. So it needs to be arranged in different rows and columns, and you have to find a way to selectively access the cells you want without disrupting everything else, right? If you create an array uh, that damages all the other unaccessed or half-accessed cells while you're trying to read into a specific cell, it's not going to be useful. So very special attention was directed by our group towards designing array level pictures for these memories. And this is one such example where this is the ferroelectric suite. By itself, it like behaves like a memory cell. However, to make sure you can still get an array functionality properly, we needed to use an extra device, which is the heater cryotron. Heater cryotron here was used more like access transistor in a 1T 1R memory cell. It is similar, but it is not exactly the same. Remember, cryotron is a current control device. So there is a lot of unique challenges that they bring in to the overall dynamics, but we managed to make sure that your array is still manageable in terms of the row access and column access and without disrupting the unaccessed cells. And the biasing scenarios and all the other details are available in our published work as well as in this table. I'm not getting into the detail of it right now for the interest of time. I don't want to bore you too much. Okay. The second approach, remember the superconducting memristor that I talked about? So I don't have to tell you that if something is a memristor, it is a memory, essentially. But the challenge is, sure, I could just throw in that superconducting memristor and say that we have made a superconducting memory that is scalable because it doesn't have inductors. If you recall my discussion a few slides back where I showed you 4 blocks of superconducting circuits and all 4 of them had inductors. And I told you all 4 of them were memory cells. So you can easily understand that these are not scalable. These are going to be bulky memory cells. So when I show you this single superconducting memristor where you have just a Josephson junction in parallel with another Josephson junction, that's it. You don't have any other extra inductors. You should be very happy about it. But what you are forgetting here is that these superconducting memristors cannot operate by themselves. You have to control them individually across the array. And to do so, you need control devices. And your heater cryotron can save the day again. These heater cryоtrons are control devices. And if you're looking at the weird structure of this memory array, that is the signature of current control. All these dashed lines that you see here, they illustrate the current flow path from one end to the other when you try to access this particular memory cell, for example, M22. And the details of how this biasing work is available in our published work. So obviously I cannot reliably explain all of these topics within the given amount of time, but I would encourage you and request you to read this work in detail if you're interested to learn more, or reach out to me. I will be more than happy to share additional resources with you. So I'm moving forward, but I want to highlight that this is a unique memory array that uses superconducting memristor as the memory cell, not the ferroelectric suite, but uses the exact same control or selector device called the heater cryotron. So heater cryotron turns out to be very useful as memory access controller. That's why I really like it. And these are some simulated characteristics. Remember, this is not experimentally uh, observed yet. This is still a simulation-driven work. All right. Uh, okay. So moving forward. However, this work that was published in Applied Physics Letter was selected as an editor speak article. So because it solved a lot of issues that the superconducting electronics folks have been struggling with for decades. Okay. So the case for something unique. So far, I've been talking about logic and memory separately. So we are trying to make memories separately and processors or logic components separately. But I'm sure you're all aware of the fact that we are living in the era of compute in memory. We no longer want to keep the processors and memory separate. We want to make sure that memories have some compute capabilities so that we don't have to do back and forth all the time and suffer from, issues like this. And let me explain what this is. On your left, you're looking at the universal von Neumann architecture that we have been using for decades. In this architecture, we have a memory block and we have a processor. Uh, they're separate, physically separate, and we have some peripheral circuitry that controls the interaction between the memories and processor. These circuits help us bring information from the memory block to the processor, and maybe after you're done processing, put back the output into the memory again. And then there is a data bus, all right? So the communication between the memory and processor takes too much time. For the most part, our processors have uh, improved in speed dramatically, but memories couldn't keep up. So there is a speed gap between memories and processor. So turns out your processors will be done with computing sooner than the memories could send you data. So you'll be waiting idle for the next set of data bits to appear to the processor. In addition to that, this data movement uh, takes a lot of energy. And if you remember my discussions in the first few slides, energy is a big issue right now. So if you could do something to reduce energy consumption, we should do that. So that's why people are more prone towards moving to the computing memory architecture, where you could make your memories capable of doing some computation, something that is repetitive, something that is done in large scale. For example, dot product or XOR or something similar to that, which is useful for certain applications. If you could do those computation within the memory cell, or sorry, within the memory array without sending it out to the separate processor block. We cannot get rid of processor because this is not a general purpose computing system. This could just do one or two types of computing, for example, but it is not a general purpose one. So you still need a processor, but if your memories are, you know, uh, advanced enough to do some computing, it could significantly speed up the process and reduce the energy consumption. All right. So that's why we're going for this compute in memory architecture. But now, I hope we are all on the same page about the need for compute in memory, but we may not be on the same page about the need for cryogenic computing memory. So let me help you with that. Number one, why would you consider doing compute in memory in cryogenic environment? One example would be, remember, cryogenic electronics require cooling, and this cooling is done in cryostat or in refrigerators, for example. And when you compute, when you use your superconducting electronics, they generate heat and they gradually heat up the overall, environment. And remember, there is a critical temperature for superconductors, and because of local heating, you could easily exceed the critical temperature and disrupt the overall system. So the way you make sure that you don't generate too much heat would be, first of all, by limiting your computing, overhead, computing workload, which we don't really want to do. We want to be as extreme as possible. Or the other way to do so would be to make them even more energy efficient by improving the architecture. If you do logic in memory, your overall energy generation because of the communication as well as the additional steps significantly reduced. And notice that if you reduce the power consumption, the coolant consumption in the refrigerators also reduce significantly. That means the fixed cost concern that you had about the superconducting electronics in general, like about cooling them down to begin with, will be much less of a problem as opposed to if you were to go with conventional von Neumann architecture. Okay, so cryogenic computing memory makes sense, but here is a different perspective. uh, Error correction is a big deal for quantum qubits. We have to do a lot of computation to make sure we could do error correction properly. One approach, one very promising approach towards correcting the qubit errors is to use machine learning. And when you do machine learning, most algorithms require a lot of dot product or other repetitive computing states. If you have to take out that information from the cryostat back to the control circuitry, I hope you remember my discussion about the back and forth communication and the noise injection. It is not going to be fun. So if you could do this within the cryostat, that means you are doing cryogenic computing memory, it will save you from a lot of noise injection, but also speed up the process. And remember, you are in a race against time. There is something called a decoherence time. Within that period of time, you have to do all the computing and finish, uh, you know, uh, your whole operation for the quantum computer. Uh, so if you could do some extra steps of computing within decoherence time, your overall capabilities for the quantum computer will also increase. So quantum computers are heavily reliant on the classical components in general to be useful. Okay, so here as well, cryogenic computing memory makes a lot of sense. So I'm going to show you one example without repeating myself of how we perform cryogenic computing memory using the unique memory device that we designed. Ferroelectric Squid is a memory device that we designed, and I just spoke about it a few slides ago. And remember, the heat attractant was the selector. So essentially, this same memory array that I talked about was also geared towards computing memory, not just memory, but also computing memory. Obviously, computing memory typically depends on unique sense amplifier design. And for cryogenic electronics, sense amplifiers are not really, off the shelf. You cannot just use any sense amplifier here, right? So we had to design these sense amplifiers from scratch using superconducting entities. So these sense amplifiers used something called Josephson junction FET, which is a transistor, but it is a very unique transistor made out of superconducting devices. Okay, so I'm not getting into the detail of that, but this is also published in our recent conference work. So using this unique combination of memory array and sense amplifier, we are able to do computing memory, specifically dot product, uh, within the superconducting memory array. So we didn't just come up with a way to design a scalable memory cell with superconducting devices. We also made sure that it is advanced enough to do computing memory, right? So enough with Boolean paradigm. I hope you could somehow relate this to the conventional CMOS-based architecture. And if you're wondering about, are there any opportunities for non-Boolean computing with superconducting systems? And I would say yes, there is a lot of opportunity out there. And I'll highlight only a few because of the interest of time. So let me start with designing oscillators because you know when you uh, when you heard about oscillator-based computing or coupled oscillator-based computing, you must have seen that oscillators could be very powerful and they could be very useful in terms of doing non-Boolean computing. So if I could give you a really nice superconducting oscillator, you should probably understand that you could couple those oscillators and do some computing, of course, right? So let me start with the oscillators first. Superconducting oscillators are very interesting. Their dynamics is unique. This is a very simple structure of a superconducting oscillators. There are more complicated structures out there. And in our group, we modeled them, we studied them, we tested them in simulation as well as in some degree of experiment. Uh, so this is essentially a superconducting nanowire, niobium nitride superconducting nanowire, and it is in parallel with the conventional resistive metal wire. And this simple combination leads to oscillation. Uh, because when you bias it with a certain current level, uh, the superconducting component takes a share of the current, and when it exceeds the critical level, it becomes resistive, and the most of the current is channeled through the other branch, and then the current flowing through the superconducting nanowire reduces below the critical level again, and it becomes superconducting again. And then it starts taking a lion's share of the current, and then again, the current level exceeds the critical level, and then it goes back. So you see a repetitive argument here, and that's because it is exactly that. There is a repetitive change from superconductor to resistive mode in the nanowire section, and that's what leads to the oscillation, all right? And in our group, we modeled the superconducting oscillators, and we coupled them. We tested what happens when you couple multiple superconducting oscillators, and we tested some rudimentary level of non-Boolean computing systems by coupling this superconducting oscillators. So this is definitely doable. What is the benefit, by the way, first of all? Most of these superconducting oscillators are extremely fast. Superconducting devices can oscillate with hundreds of gigahertz. So you see, you get the speed benefit, but also every oscillation, the energy associated with every oscillation stage is orders of magnitude lower than semiconductors. So in general, superconducting switches are extremely energy efficient. That's why if you could use switching in the superconducting oscillators instead of semiconducting oscillators, you get a lot of benefit in terms of energy as well as speed. Okay, now here is a different perspective. Uh, Neuromorphic computing. Those of you who are aware of neuromorphic hardware and neuromorphic computing, you know that the primary target in terms of hardware design for neuromorphic computing systems is to design artificial neurons and artificial synapses that behave like human brain, the biological brain per se. Okay? But there is an argument where doing superconducting neuromorphic system makes a lot of sense. And here is that argument. Uh, think of our human brain. We have many neurons in our brain. To be exact, we have 86 billion neurons. But if you follow the field of neuromorphic computing, the best available neuromorphic processor from Intel, for example, Loihi 2, it has only 1 million neurons. So it is nowhere close to the level of connectivity that the human brain achieves. But why is that case? Why can't we just get to billions of neurons and connect them the way our human brains are wired, right? There are multiple reasons. One of them is interconnect drop. So when you have a really big neural array with semiconductors and you connect them with metal wires, these are not ideal. They have resistive drop. And if your array size is too big, at some point, you will lose your voltage bias. And towards the edges of the array, you almost have, no useful voltage at all. So you cannot really have arbitrarily large synaptic arrays. You have to break them down into smaller chunks. So with semiconducting systems, which are lossy, which are resistive, you cannot really uh, approach the level of connectivity that human brain achieves. And that's one thing. But also, there are some other. So, in terms of scalability, we can never really reach the biological brain level complex connectivity in our human brain, in our electronic platform. So that's why neuromorphic hardware will always lag behind the biological brain. So we will never know, possibly, unless you switch to something that is inherently dissipation free. And I don't have to tell you more. Superconductors have zero resistance. So if you could use superconducting neurons and superconducting synapses and connect them with superconducting interconnect and get a really arbitrarily large array size, uh, that might lead to more complex neuromorphic array. And who knows what kind of applications that can enable. So this is at a stage where we are still exploring, and many entities, including universities and national labs, are involved in the search, and they're looking for neuromorphic systems made of superconducting and other cryogenic entities. All right. And in addition to that, the conventional energy benefit of doing cryogenic AI. So neuromorphic computing is a form of AI, for example. It is a form of AI hardware which is inherently energy efficient. If you do it in cryogenic environment, you are getting even more energy efficiency because of the superconducting nature of it. So you're getting more like a double-edged sword, for example. Okay, so this is the vision. Make neurons out of superconducting entities, make synapses out of superconducting entities, and then connect them in hardware to create a superconducting neuromorphic hardware. This is the vision. And this is work from our group. We design, obviously, the previous slide showed work from a different group. It is also a published journal. So we are not the only ones working on this topic. But this slide shows you, excuse me, published work from our group. And I want to highlight the devices that I talked about already. So this symbol stands for superconducting memristors that I mentioned a few slides ago. So using superconducting memristors, we developed a unique superconducting oscillator, which is programmable. So the oscillation frequency could be programmed by programming the superconducting memristor. So this is one oscillator, this is another oscillator, and you are basically coupling these two oscillators. And what you're getting here is a spiking neuron. So you can create a spiking neuron, which is programmable by individually programming these superconducting memristors. So you could program the spiking frequencies of these neurons and get some unique advantages when it comes to designing algorithm for neuromorphic systems. And the H-tron is also sitting there to help with this programming process, individual programming of the superconducting memristors. So you have pre-neuron here, you have post-neuron here, and what you're looking at in this section is a unique synapse design. And by the way, we have patents, US patents for this synapse. This synapse architecture uses heterocraton and superconducting memristors as well to achieve different levels of synaptic weight, which I'm not getting into the details of because all of these are published in our recent papers. Okay, so last but not least, some of you must have heard about probabilistic computing. This is more like one of these up and coming paradigms of computing, which is not quantum, which is not fully classical, which is not oscillator based non-Boolean system. It is not neuromorphic computing either. It is something else, right? So probabilistic computing, or PBT, is between quantum and classical computing. The first thing, if you follow this field, the first step towards doing probabilistic computing is to make a p-bit or a probabilistic bit, right? So how can you do this probabilistic bit? How can you make this probabilistic bit? Well, one approach is to use superconducting devices, obviously, because my talk is about superconductors, as you see. Uh, Together with one of my collaborators from University of California, Santa Barbara, we were thinking of ways to design probabilistic bits with superconducting devices. And we noticed some inherent probabilistic switching in devices like cryotron. So they're heavily influenced by thermal, uh, interference, and heat is inherently stochastic to some degree. You cannot definitively control the level of temperature that the channel gets uh, by the heat injected by the gate, because there is always some environmental uncertainty. And if you design it well enough, you could make it into almost like a probabilistic switch. So what you're looking at here, this is the experimental data. This is a recent work, still unpublished, under review currently. But it shows the first step towards developing probabilistic bit with superconducting devices. So this is another up and coming direction towards superconducting electronics, where you could also do probabilistic computing with superconducting entities, right? So last but not least, I want to highlight few other technologies that are like superconductors, meaning they are dissipation free, but they're not superconducting. And I will show you their unique promise. So the one that want to talk about is topological insulators. So here on your left, you're looking at a structure called twisted bilayer graphene heterostructure. So basically you have two layers of graphene and they're twisted with respect to each other at a really small angle, which is known as the magic angle, right? 1 point something degree, 1.03 to be exact. It's a very small angle, but that does the magic. That's why the name magic angle. That creates some unique properties. Basically, the structure demonstrates quantum anomalous Hall effect. Um, and that leads to properties like this. If you see this graph on the right-hand side, uh, you have a hysteretic switching property between two Hall resistance states, which are quantum mechanically protected. By the way, look at the unit on the y-axis. It is h over e square. So both of these are, universal constants. So they don't change with anything. They're not function of temperature or anything else. So essentially, you have two resistance levels that are quantum mechanically protected and constant. They will not be functions of temperature or any other aberration. And you can switch between them by exceeding certain critical current to go from one resistance state to the other, and you can switch back by exceeding a negative critical current on the other side. So this hysteretic switching looks similar to a ferroelectric, as you can think of, but the difference here is between these two switching levels, there is absolutely zero variability. Okay, in addition to the other feature, uh, topological insulators provide dissipation-free conduction through the edge states. Through the edge, you have basically zero resistance electricity conduction. But in addition to that, you have zero variability resistance levels. I hope you can easily see that this could be shaped into a memory. And we also saw that, and we use this device to design a unique cryogenic memory array with, this quantum anomalous Hall effect devices as the memory element. And this is the symbol of the device that I just explained. And the orange boxes that you see here, they are a material called MIEC, mixed ionic electronic conductors. And these are just used to select these cells individually and make sure this is more like a crossbar kind of architecture, similar to what you have seen in other conventional emerging memories. But the uniqueness here is that the memory element is quantum anomalous Hall effect device, a twisted bilayer graphene. And for that, you need to use and design specialized voltage amplifier and voltage comparator, of course, which we're not really talking too much about today. But in general, that gives you the additional feature of zero variability in addition to the other benefits of cryogenic memories. Okay. So just wanted to also highlight that we use the same memory array and we explored its logic in memory functionality, and apparently it is doable, because any memory that doesn't have logic in memory feature nowadays is less attractive in today's standard. We had to find a way to do logic in memory in this technology as well, and we did that. This was the first, one of the first demonstration of cryogenic logic in memory. And the point that I wanted to make here is, remember, between these two resistance levels, there is absolutely zero variability in terms of the resistance level. There are variabilities in other things. However, think of a memristor, conventional memristors, which has low resistance and high resistance state. But low resistance state is never just a level. It is a distribution. Similarly, high resistance state is always a distribution. It is not just a level, right? So there will be variability coming from the resistance levels themselves, and there are variabilities from the biasing and all the other aspects of the circuit, right? So you're dealing with a lot of variability. But here, the memory cells themselves provide you with two completely constant resistance level. So you don't have to worry about this source of variability, but you worry about the other sources, but not this one. Okay. And also something that I didn't highlight here, the Hall resistance states, if I go back here for a second, the reason why they're shown as positive and negative resistances is because the way the Hall voltage appears, the Hall voltage polarity flips, right? Basically, and we represent that using resistance, essentially positive and negative resistance. But you could also use positive and negative polarity of the voltage, essentially. So the fact is, you don't just have two voltage levels, you have two opposite polarity as well, so which is much easier to sense. And we did Monte Carlo analysis with these memory cells to make sure that we find the realistic distribution. And you get a lot of benefit because of this reduced variability in these memory cells. Okay? So that brings me to the end of my talk, and I want to talk about few future directions and future needs in this paradigm of superconducting electronics. I would highlight on three topics: co-design, need for synthesis and automation, and prospect of commercialization and workforce development. First of all, I want to highlight that you are dealing with a lot of complex devices, and the circuits that come out of these devices are going to be unique, and their features and limitations will be very unique as opposed to anything that you know of. So co-design is the key. Without co-designing across devices circuit systems, we will never get the full picture. And that's what we do in our group quite a lot. For example, we start our work at the Josephson junction level, which is a device. We make models of these devices and test them thoroughly through experiments and simulation. And then for example, once you have a model of a Josephson junction device, you can have two Josephson junctions in parallel. You can do a model of that as well and test whether that model gives you what you want, and then eventually do an experiment test out at some point. But at least once you have the model for the Josephson junction, you can then test out parallel connected Josephson junction and explore the sweet structure, or for this case, superconducting memristor. Once you have a model for the superconducting memristor, you could then use it. So this is the superconducting memristor. Maybe you can borrow the model from here and put it into the oscillator structure and test out the oscillator behavior. And once you know the oscillator behavior, you can then couple these two oscillators and shape them into a neuron, for example. So you could gradually build from a small scale device to a bigger scale device to a small scale circuit to a bigger scale circuit and to a system eventually. So that's the beauty of co-design. That's the power of cross-layer co-design. Okay, I want to also highlight the need for design automation. Obviously, CMOS electronics benefited a lot from design automation, or EDA in general, electronic design automation, for decades. We need something similar for superconducting electronics as well. We have been doing something like that in collaboration with our colleagues from uh, Technical University of Munich um, and RPI, Rochester Polytechnic Institute. And we want to continue that work. What we do typically is we make device models, uh, shape them into compact model, use those compact models to make logic gates and memory cells, and we make standard cell library out of them. And once we make standard cell library with these superconducting entities, we can then use synthesis to essentially create a system like the socket for a high performance computing system, and then do some large scale benchmarking, like for example, lean pack benchmarking for supercomputers. This is something that we have been working on right now. We have some preliminary publications, but not to the level that we are, we would like to have. So we are currently, this is a work in progress per se. Finally, I want to highlight the market opportunity here for those of you who are considering the financial side of it. Apparently, superconducting electronics is not going to remain a small niche anymore. It is hopefully going to explode because of its possible use cases across so many markets. If you think about high performance computing, the overall market size related to that is like easily beyond $30 billion dollars. And my assessment, obviously, I'm not a finance expert in any way, but my students and I, we did some rudimentary calculations. When we think together, high performance computing, aerospace, and quantum computing uh, can have more than, almost 50 billion, more than $50 billion of total relevant market share for superconducting electronics in the near future. So if we do it right, it's going to change the game, both financially as well as technologically, and in other ways, of course. So it is something to be taken very seriously. In terms of timeline, this is my personal opinion. I think for the next few years, 2 to 3 years, we will be focusing mostly on simulation test bed, and many other research groups are exploring something similar. And within 5 years or so, prototyping and benchmarking will take the center stage. And within this decade, I think we'll have a scalable superconducting systems. So actually, that's our target in general. Maybe sooner, but at least within a decade, we want to get a scalable superconducting systems that can be deployed for real applications. And for topological electronics, the one that I covered in the end, I, I think this is more futuristic and it will take a while because it is difficult to make multiple devices. At this point, we can make one prototype, for example, but not too many. Not when I say we, not necessarily our group, other research groups who are working on this material science aspect of this topological electronics. Uh, Hopefully, they will find a way to make many devices in a reproducible way. But that's why I'm putting it more than a decades out, essentially. Okay, so with that, I hope I was able to convince you about the needs for superconducting electronics and the unique opportunities and the challenges and the way we try to find solutions to these challenges. Because we believe in what Einstein quoted, the true sign of intelligence is not knowledge, but imagination. We are trying to imagine the future. We are trying to find a problem that needs a solution and try to imagine new solutions to those old problems. I hope we get to collaborate at some point. If you're interested, don't hesitate to reach out. Before I conclude, I would like to acknowledge support from my sponsors, National Science Foundation in the US, Department of Defense, Department of Energy, and acknowledge support from all of my collaborators across many universities and national labs, and also acknowledge the dedication of my graduate students and undergraduate students. And thank you all for listening. And if you have any questions or comments, don't hesitate to reach out to me. You can find me, if you can scan this QR code and get to our website, or you can just Google my name, and hopefully you'll find our website as well. More than happy to answer emails if you have any questions. I will also try to make myself available over Zoom to answer live questions in the session. Thanks again. Take care.